professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today we'll talk about static structural analysis of a stepped bar. The bar is consisting of three different cross sections, and each one of them having length equal to 100 mm, and the cross sectional radius, the big one is having cross sectional area equal to 2500 mm square, the middle one is having cross sectional area equal to 1600 mm square, and the smallest one is having cross sectional area equal to 900 mm square, each one of them having length of 100 mm. So what we have to do is we have to make the left side, that is the big cross section, they should be fixed, and at the right hand side, that is on the end of the smallest cross section, we have to apply a load of 5000 Newton, right? We'll analyze this one using ANSYS mechanical APDL. Okay, then let's get started. First of all, what we have to do is we have to open a folder in the desktop, and all works should be saved there itself, right? We'll make a folder in the desktop by the name of Step Shaft. Step Shaft, the folder is open. Next part, we have to start with the change directory, and by browsing we'll go back to the folder what you have created right now. Step Shaft. Okay, all works, what we will do, that will be set in that folder. Okay, next part is we have to change the title. Title is given as FEA, tapered bar. Okay, done. Now what title we have given, when you see this one in the lower left corner of this screen, so plot, replot, it will show in the lower left corner, tapered bar is same. Okay, now while doing this experiment, we have to start from top to bottom from here, right? We start from in finite element analysis, we have to follow three different stages. One is pre-processing, then processing, and finally post-processing. In pre-processing, we'll have to provide elemental properties, material properties, boundary conditions, modeling, etc. And in processing, we have to solve it. And finally, in post-processing, we have to get the results, analysis, plotting, etc. to be done. Right? So we're starting from preferences, that is pre-processing. This is a static structural analysis, so we have to click structure 1. Okay. Next one is pre-processor. Element type, add, edit, delete. Nothing is different, so we have to add it. Now here, from the elemental table, the link and beam both can be taken. And remember one thing here, the element type reference number is 1. This one will be required while providing elemental table. In elemental table, this number is very important to know, right? Okay, close it. So we are considering link and default 3D finite strain. Okay, close. Now next one, real constants is not required for, real constants is actually required for providing areas and other things, and in case of beam and link, real constants are not required. So we'll start from material properties. Material models, structural, linear, elastic, isotropic. So it is actually material number 1, we are providing modulus of elasticity of the first material. Let's that one be 2.5 E5, and Poisson's ratio equal to 0.32. Okay, first material is done. Now again we have to apply second material. So you come from material, new model, material ID is 2. Okay, then isotropic, Poisson's ratio will take 0.3 and modulus of elasticity will be 2E5. Okay, so modulus of elasticity 2E5 and Poisson's ratio 0.3. Okay, second material also provided. Now the third material, again from material, new model, material ID is 3. Okay, so we are providing modulus of elasticity equal to 1.9 E5 and Poisson's ratio 0.26. Okay, all material properties provided, right? We'll close it. Next one, we have to see the areas. It will come from sections. As we have taken link, so we have to start with link, add. Now it is asking ID number. You can provide ID number as 1, but as we are having 3 different cross sections, so we will be having different IDs, ID number 1, 2 and 3. Okay, ID number 1. Let's provide the section name is big section, and area of the bigger section is equal to 2500 millimeter square. Okay, apply. Now second ID is the intermediate one. Let's take the ID number is 2, and section name is middle one or medium you can provide, and the area should be 1600 millimeter square. Apply. Then third ID, the smaller one, it will be small area, and we are providing the area equal to 900 millimeter square. Okay, all areas have been selected. Okay, next part we have to start from modeling. Create nodes, active coordinate system. Now here the first one is node numbers. These will be created automatically, like one number, net number 1, 2, 3, 4, etc. We need not provide any values, it will be done automatically. The next one is location of nodes. As it is a one-dimensional problem, so we need to bother about only X location. Y and Z is not required at all, right? So in our case, we are having the total length of bar equal to 300 millimeter, and first node will be created at origin, second node will be created 100 millimeter away, third node will be created 200 millimeter away, and the final or the last node will be created at the 300 millimeter away, right? So I am selecting the first node at origin. So 00 value is not required. By default it will take 0 values. Apply. That means first node is created at the origin. Now second node we have to create at 100 millimeter away. Apply. You can see second node is already created, right? Now third node, to apply 200 millimeter away, right? Third node is done, 200 millimeter away. Then last node will be 300 millimeter away. Okay, so we have created 4 defined nodes. First node at origin, second node 100 millimeter away, third node 200 millimeter away, and the fourth node 300 millimeter away, right? Now these nodes will be connected in the form of lines or elements, right? That will come from elements. Now while connecting, we have to see that all these elements will be having different cross-sectional areas, right? And how to change these cross-sectional areas? That areas we can see from elemental attributes. Element attributes, see, you can see material number is 1 and section number is 1. There is big one, right? We are selecting that one, and under this cross-sectional area we join node number 1 and 2. 2 nodes. We join node number 1 and 2. Okay, that means first cross-sectional area and first element is done. Next one, again you have to change the cross-sectional area, so it will come from element attributes. Material number should be 2, and it will be the medium cross-sectional areas. This is selected. Again the nodes to be connected through nodes. We select node 2 and node 3. Okay, done. Now the final one, again we have to move to element attributes. It will be material number 3, and it will be small cross-sectional area. Okay, now the nodes to be joined or connected through nodes. Select node number 3 and node number 4. Okay, done. Modeling is done. That means we can say that first element is in between node number 1 and node number 2, that is having cross-sectional area equal to 2500 meter square. Second element in between node number 2 and node number 3, that is having cross-sectional area equal to 1600 millimeter square. And the last element is in between node number 3 and 4, is having cross-sectional area equal to 900 millimeter square, right? These are the defined nodes, right? So our modeling is done. Next part we have to apply boundary conditions, right? We start from solution, analysis type, new analysis, static structural analysis. Okay. Next, define nodes, apply structural displacement on nodes. Now in this case, our boundary condition should be left hand side should be fixed, right? So we select the left hand node, that is the first node, okay, and it should be zero displacement from x, y, z all directions. So all degrees of freedom selected, and displacement should be zero from all directions. That means it is completely fixed. If you don't provide any value, it will take by default zero values. So okay, that means left hand side is completely fixed, it cannot move right now. Okay, now the final thing, we have to apply load or force at the node number 4. So force a moment on nodes, select node number 4. Okay, Fx, that is force is being applied in the x direction, positive direction of x, and the value of force equal to 5000 Newton. Okay, now suppose we want to apply force in the opposite direction, then it will be minus 5000, and again we can apply x, y direction also. If we want to apply force in the upper direction, maybe instead of fx it will be fy, right? And if it's positive, then it will be upward direction. If it's negative, it will be downward direction. Okay, in our case we are applying force in positive direction of x-axis, that means positive force, and the amount of force equal to 5000 Newton. Okay, that force is applied. You can see the red color is indicating force of 5000 Newton. Everything is fine, perfect. Now we have to solve it. That means processing is required. Pre-processing is complete, right? We have to start from solving. Solve current LS. If everything is right, it will show solution is done, right? Let's see. This solving, solution is done, so everything is perfect. We can get the results right now. So our task is to go for post-processing, right? To see the results analysis, and the plotting of this can be done from here. So it will be done from general post-processing, right? First of all, you see plot results, deform shape, deform plus undeformed. That means it will show the original drawing plus the deformed drawing. By the application of force, the object will be deformed. That one also you can see. Okay, this is the drawing, but this one is not perfectly visible. If you want to see in a better way, you can change it to a 3D object, right? It will be done from vertical tools, style, size and shape, and display of elements should be on. Okay, now see, this is the object. Now to view this one in a better way, we can make this a symmetric view. Isometric view can make it. See, this is the thing, right? Now here it is very clear that first node is having zero displacement. Here the object is fixed. Second node is having very small displacement. Third node is having more displacement, and the final node, the fourth node, is having more displacement, right? This is the form deform shape. Okay, next part we have to go for contour plot. Want to see displacement x direction, nodal solution, DOF solution, x component of displacement. We can see yz also, but it is a one-dimensional problem, so better to see only x direction. Yz will have nothing, right? So x component of displacement. See, this is the answer for x component displacement, x direction. That means in x direction, 3 defined nodes have. We can see the displacement of 3 defined nodes. The first node is having zero displacement. Second node is having displacement of 0.001175. Third node is having displacement of 0.003524. The final node is having displacement of 0.005286. Right? These are the displacements. Now we can see the same thing in case of listing also, right? Another thing is equal. We see elemental solution. That is what we see stresses. Stress. One is stress. Okay. You can see here maximum stress developed equal to in the element number 3, and maximum stress equal to 5.55 megapascal, right? Element stress. Okay. Now we can do another thing, like what values we have seen. You can see in the form of listing also. List results, nodal solution, develop solution, X component of displacement. Right? So we can see first node is having 0 displacement, Ux, that means in the direction of X. Second node is having displacement of 0.8 10 to the minus 3. Third node 0.23 10 to the minus 2. And the fourth node is having displacement of 0.52 10 to the minus 2 millimeter. Maximum displacement is on node number 4, that is equal to 0.52 10 to the minus 2 millimeter. Okay? Again, the same thing, that is the stress value also we can check it from modular solution. It will be in the form of listing. So we can see stress, one is stress. Okay, it is showing maximum equal to 5.55, right? First element is having stress equal to how much? First element is having stress equal to 2 megapascal, second element 2.5, third element 4.3, and last element 5.55 megapascal. These are the stresses in case of listing, right? Okay. Now another thing can be done. We can see the stress values by forming an elemental table, right? How can it be done? So we'll see element table, define table, add, we have to add the value of stress, and we have to drag it down, select by sequence number and ls for stress. We know that element reference number is 1 at the beginning while providing element numbers, element identities. We know that element reference number is 1. Okay, okay, close. Now see plot element table. Stress, we can see stress is 5.55 megapascal. Stress value equal to maximum value equal to 5.55 megapascal, right? So different elements are having different stresses. Now see in the form of listing, list element table. Okay, again you can see first element table. You can see the first element is having stress equal to 2 megapascal, second is 2.12, and third element 5.55 megapascal. These are the stresses, and maximum stress developed equal to 5.55 megapascal. Okay, so this is all about finite element analysis of a stamped bar using ANSYS mechanical APDL. Okay, if you like this video, please subscribe and share, and if you have any kind of doubt, please write to me. Thank you so much for watching this video. Thank you again.